All right, let's make sure the audio is good. Perfect. All righty. So we will go back over here, go back one. All right. Good afternoon, everybody. My name is Ethan Hoven. I'm the president of the UH chapter of Eta Kappa Nu, the Electrical Engineering Honor Society. We work with IEEE. We're partnered for with IEEE for this event. So this is our Tech Talk series. We've hosted several of these so far. This is the third semester running. So quick show of hands, who's been to one of these before? Any of them? Got 1, 2, 3, 4, 7, 5. All right, cool. So who was at the stealth one last time? The one that I gave previously, so we got one person. All right, cool. And you, all right, cool. So this is a long time coming. It was meant to happen a semester ago, but got busy, but now we're here. So this slide deck is the follow-up, functionally, to the stealth. It's a standalone deck on its own. You don't have to have attended the previous presentation to understand what's going on. But when it comes to stealth technology, ultimately, the most important technology is actually just electronic warfare technology. That's what actually keeps our planes in the air, keeps things from getting shot down, and keeps things from getting detected. So, little bit, if you haven't signed in, I think everyone's good. You just came in. You can sign at the end, it's fine. Yeah. All right. So, who am I? First and foremost, I'm a graduate of the UH Electrical Engineering program here. Started in 2019, graduated in 2023 with my undergrad. Anyone here have Dr. Beal for any classes? The GOAT. The GOAT. Currently working on my electrical engineering master's degree here in a part-time capacity. Getting close to finishing that, which is great. And looking to do a PhD at some point. Don't know if it'll be immediately after. So we'll see how that goes. In terms of full-time employment, I'm a full-time Tempest engineer at Northrop Grumman. If you want to know what Tempest is, talk to me after. I'm also a self-proclaimed habitual project collector. In addition to my education and my studies and my work, I also maintain a large litany of home projects and hobbies, and it's a very good time. And you can see some of them in the pictures there with the comical explosion and the laser. And it says rocket enthusiast there, which is fine too. All right. So, to begin, what to expect. There's going to be a disclaimer. For all the ones I do, because it's DoD adjacent, I have a disclaimer at the beginning just so I don't get hit by the ITAR police. And then we're going to go on through. I'm going to give you a brief surface level introduction to just what is electronic warfare, what are the terms, what are the relevant fields, where is it used, what's its history, that kind of stuff, basic principles. And then I'm going to go into the 3 primary topics we're going to talk about tonight. Of those 3, this slide deck really just became an electronic countermeasures slide deck. There was too much to smash into one presentation. So for the most part, we're going to be talking about electronic countermeasures, also known as electronic attack measures. So this is an offensive method. I do have some slides on electronic countermeasures, and I will discuss that briefly, but there's a lot there, and that works better as its own slide deck, which I will do in the future. And then there is a slide on electronic support measures where I say I did not make slides about electronic support measures. And then at the end, we have a Q&A if there are any questions. So to begin, we'll hit the disclaimer. I, in a professional capacity, have not done any work on electronic warfare technologies, so I can't leak anything, I promise, which is very important. All the information I'm about to present is accessible to the public and is open access. The main source of all the information for this slide deck is this text right here. It's an AIAA Education Series text. It is Radar Electronic Warfare by August Golden Jr. This is an excellent book. I highly recommend it. And if you are an AIAA member, you can get it 15% off. I think it's like $60 if it's 15% off. Pretty good. Additionally, electronic warfare is a hot topic in the Department of Defense, and it only gets bigger. If you just kind of look back in time, you'll see a lot of people were really focused on, stealth and shaping and coatings, and then the second like a radio could like kind of fit into like the size of like an iPhone or a handheld, everyone's like, we don't really care about stealth coatings anymore because they are nowhere near as effective. But here's the thing. While you may be enticed after I tell you that you can in fact do this at home for a relatively inexpensive price, you shouldn't do it. The FCC and your local hams will come to your house and they will kill you. And you'll get a really big fine. So it's not worth it. If you are going to do it, you either have to do it in a professional capacity or invest a lot of your time and money into building a shielded enclosure that is up to mil standard. I don't recommend doing that, but it is a fun hobby. All right, so let's begin. What's the deal with electronic warfare? So this is just an image off Google, but it's very illustrative of how horrific any type of scenario is when it comes to signals in the electromagnetic spectrum. Everything we do in the modern day has electronic signals, is making use of the electromagnetic spectrum in some way, shape, or form. And really, at the end of the day, when it comes to conflict, anything like that, communication is king. That is literally all that actually matters. Communication and control. And information is king, really, but that all kind of wraps into one. So, as you can see, this is the type of stuff you'll see if you're running a con ops or some type of trade study for the DoD. You're going to see these types of images, and they never make any sense. They're not really meant to. It's just kind of like, ooh, generals like, ooh, planes. So that's kind of how it goes. But generally, any act of intentionally making use of the electromagnetic spectrum in an offensive or defensive manner is generally referred to as electronic warfare. But that's just kind of a general overall arching term. There are better terms. Technically, it is electronic combat, which encompasses electronic warfare, which is itself command and control communications countermeasures technologies. So that's denying any types of comms, any type of control, your GPS, that kind of stuff. And then you also have the most important, and often in a DoD capacity, the one everyone cares about the most, is SEAD, suppression of enemy air defenses. All of this, at the end of the day, is really just a really fancy way to turn off people's radars. That's all that matters at the end of the day. If you do not have a radar, I can do whatever I want to you. You can't stop me. And that's kind of how modern militaries operate. It's all about detection. Sensors matter leagues more than any possible effector or missile, unless it's a nuke. Then it's, whatever. You're gone. All right. So, for those who are not familiar, I hope everyone is, but it's okay if you're not. This is the electromagnetic spectrum. And basically, when it comes to electronic warfare, we're operating in this domain, really this domain predominantly, a little bit over here, and sometimes if you're like really classified over there, but we don't talk about that one. And basically, radio waves. That's all we really care about. There is an increasing emphasis and popularity in electro-optic IR systems. They are becoming more powerful, but there's only like 4 countries who can even afford to do it. Us being one of them, it's a very good hobby, or it's a very good career to get into. UH has an optics focus, and if you do have the option to take some optics classes, I highly recommend it, because really the same tricks that we use in EW, electronic warfare in the radio domain, apply in the optics domain. It's just like way more expensive. Brief history. Funny enough, the first ever electronic warfare instance happened all the way back in 1899 in the Second Boer War, when the British attempted to flash Morse code with a lamp onto a cloud, and the Boers were like, they're trying to talk, so they blocked it with their own lamp. So that was the first ever instance of known electronic warfare, us using the electromagnetic spectrum, in that case just light, to suppress enemy communications. Good on them. Obviously, though, that's a pretty niche case. So the most common and really the first actual instance of electronic warfare is in, World War I. Radios became a pretty important part of the military, and they very quickly realized that if you suppress communication while you still have communication, it's a lot easier to surprise your enemy, encircle your enemy, just kind of beat them. So very quickly, people realized how to make jammers. Things that are loud, annoying, and hard to handle. And back then, with an analog radio, or really just like a non-digital radio, a jammer, you're done. The second that thing happens, there's very little you can do besides hopefully hopping spectrums, but again, they weren't very tunable, they were not very adaptable. We're talking vacuum tubes, this stuff wasn't amazing. At least not amazing in 1904. So, now we're gonna start breaking it down, and don't worry, I know you're all excited for it, the math is coming. So, principles of electronic warfare. There are really 3 main topics we care about ESM, electronic support measures, often you hear this referred to as SIGINT. This can happen live in a theater of battle, but often SIGINT is done months, years, decades in advance. This is your surveillance of enemy capabilities, what frequencies are they using, where are their radars located. All this types of information is extremely useful and is actually, as you'll see when we get to the math, necessary. You need that information in order to synthesize an optimal attack or defense measure. Then we have electronic countermeasures, and you'll notice the next one says electronic countermeasures. There's a bit of confusion there, so I'll try and clarify this very quickly. Electronic countermeasures is I attack you. It is electronic attack measures. Electronic countermeasures is defending against electronic countermeasures. So in this case, an anti-drone ECM system, you guys may have seen some things like this. They're handheld YIGI or directional antennas, and they use them to blast drones out of the sky by suppressing their GPS or their control signals, jamming basically. And then technically, a electronic countermeasure would be a home-on-jam AIM-120 AMRAAM. So basically, we do in fact have missiles whose sole purpose is to be like, oh no, I'm getting jammed, and for certain types of jamming, you are just a beacon, and you're giving yourself away. So we can just send a missile that tracks the beacon. You're not going to jam them for very long. So, I mentioned at the beginning, but I'll reiterate it here. Electronic warfare and stealth are about one and the same at the end of the day. Stealth, or low observables, is a blanket term to basically say, my job is to reduce the detection probability of my vehicle. The most common and the most interesting ways that's done is shaping, material composition, things like that. But the most effective way it is done is with electronic warfare. It's the penultimate stealth capability. F-35s, F-22s, B-2s, B-21s, every platform, F-15s, F-18s, every single platform that is stealthy isn't really, they have excellent stealth coatings, they have excellent stealth shaping. Their basic radar cross-section without any active ECM, electronic countermeasures, is excellent, but not enough. Modern radars are just too strong. If you try and rely solely on RCS mitigation or minimization, you will get shot out of the sky. Electronic warfare is what makes up the difference. This is actually how you can basically do what you want to do while in enemy airspace. So, also, I say it there, we're going to talk radars. That's the most common application. Obviously, you could jam radios, you could jam remote controls. You're in Ukraine, you want to jam drones, that's fine. But the most common and the most popular for careers in terms of electronic warfare is suppression of radars, or deception, or defensive radars. You can have a whole career of just electronic countermeasures. So, scope, we're going to discuss the principles. So we're going to hit publicly available information on the math, basic formulas. We're going to talk several types of jamming techniques, a couple types of defense techniques, and we're not going to talk about support measures because I don't have enough time. Again, so now we're at ECM. So this is the first major one, and this is where we're going to spend the most of the time in this slide deck, is electronic countermeasures, also known as electronic attack measures. ECM can be broken down into the following figure. So we have electronic countermeasures, two types, active and passive. Funny enough, observable reduction, aka stealth, is just a passive electronic attack measure because you are manipulating the electromagnetic spectrum to reduce the effectiveness of an enemy radar. It technically counts. Passive, so we have stealth, observable reduction. Clutter enhancement, we'll talk about this more. Basically what this means is you dropped a bunch of chaff into the air and now it's impossible to tell what's going on because they're seeing way more reflections than they expect. And then, this is where a lot of the math's going to come in for tonight, active countermeasures. And there's two main varieties, noise-like and target-like. When we think noise, think static. That's a good representation. When we say target-like, that's where it gets interesting, and that's where the money's at. So, keep it going. We're going to start with noise-like jamming. This is the most common type, and it's been around the longest. It's kind of easy to make noise. Realistically, you could just have an amplifier with nothing connected to it, and it would have noise and just blast out into the environment. But The primary goal of noise-type jamming techniques is to overwhelm target sensors. Your hope is that they can't see anything. This has weaknesses, and we'll discuss why there's weaknesses, but basically your purpose is to be louder than anything else could ever be. So you're basically just screaming really loud into their ear and hoping they can't hear, someone telling them a bank number or something. So there are many types of noise jamming, and this isn't even close. There's hundreds. There's new ones that are created every single day, but some pretty common ones: continuous wave spot noise. Whenever you see something like spot, think a narrowband solution. There's a large spectrum. You can broadcast anywhere in there. If you're doing spot jamming, it means you're just focusing on one narrow area. Spot jamming is useful in the case where you don't want to jam yourself. Not a good idea. Continuous wave self-screening, that's where you're doing sweeps across the full spectrum or some selected bandwidth. Then you've got amplitude modulated, average center frequency variation noise jamming, polarization modulation noise jamming. There's a whole bunch of tricks and additions you can make to this. And I'll discuss a bit later on with the target, like why polarization, frequency, amplitude, why these things matter, and why they're actually super cool, because you can actually create synthetic and fake signatures and targets by tweaking these types of parameters on signals. And note, these can also be used simultaneously. You don't have to just pick one. You could use multiple at once, you could swap between them super fast. Really up to you, and it depends on what you're trying to suppress, what their capabilities are. If you're fighting someone who has commercially bought radars off Amazon, you could really use any of these and beat them. If you're fighting a country who has some semblance of a defense budget, different story, noise jamming probably won't actually work at all. Math. So, the whole point of this, we're going to go through and we're going to derive some fundamental formulas and concepts for noise-like jammers. Technically, this is only talking about spot and continuous wave self-screening, but those are the predecessors to everything else. All the other jamming techniques are built up off of those fundamental ones. So, first step. Are radars continuous or pulsed? The answer is both. It depends what we're talking about. But most commonly, radars are pulsed because it's less expensive, it's less complicated. If you have a continuous radar, that means your power handling has to be obnoxious. If you have a pulse system, you can have a large average power or pulsed power without, breaking the bank or frying your circuits. So in this case, we're talking about pulsed systems here. To begin, this little formula is just talking about the average power of some given jammer. So the power of our jammer, whenever you see J, any subscript, we're talking jammer. When you see subscript R, we're talking about the target radar, what we're trying to jam. And that's a blanket rule for every single equation. Simply equal to a summation of pulses over some amount of time, however many pulses you did, sum them all, that's your average power. And of course, divide by the sum, standard average. Nothing crazy there. And then we're going to get to this assumption. First assumption, the jammer pulses have the same frequency, that's misspelled, as the target radar. Then, if they have the same frequency as the target radar and the same pulse rate, their bandwidth is the same. So the bandwidth of the jammer is equivalent to 1 over the pulse time of the jammer, pulse separation, because, what is a frequency if not 1 over time? And the bandwidth is narrow. If these are the same, the pulse time separation of the jammer and the radar, then, of course, based off this rule, that means their bandwidths are the same. This is just a basic derivation. It doesn't really matter. You don't need to think about this. This does come in later. In real life, your bandwidths are almost never the same. Your jammer almost always has a larger bandwidth than the radar. And literally next slide, I just get rid of this and we talk about that instead. So our first formula, the average power of the jammer received at the radar. All of these formulas are going to get us to what's called a jamming to signal ratio. And then we're going to be able to use that to derive what's called a burn-through ratio, or a burn-through distance. All to say, by the end of this next couple slides, I will give you a single formula, and you can plug in the parameters, and based off those parameters, you can calculate the exact distance at which your vehicle with a jammer is invisible. And once it goes past, it is visible. That's your limit. That's what you use for mission planning. That's what you use for vehicle design. That's everything. That's called a burn through. So this is all what this is, just to give you guys a full picture, because again, not everyone likes math. So whenever you see RJ subscript, that is the power of the jammer received at the radar. So it's where they meet, which of course is at the radar. All this is it ends up being the power of the jammer times the gain of the jammer antenna. When we're talking jammers, hopefully you're not just emanating a jamming signal in every single direction. One, you jam yourself. Two, that's inefficient. You want as much of your jammer energy to be at your target. So we have directive antennas, phased arrays, horn antennas, stuff like that. Whenever you see the gain with a subscript J or gain with a subscript R, that is simply the multiplier, the gain of the antenna in the direction we're talking about. It's just a unitless value, but think of it as a multiplier, where if you were emitting in all directions, you have a gain of 1 everywhere. You pick up the same signal strength anywhere you are around the antenna. If you have a very directive antenna where it basically shoots a laser beam in one direction and nowhere else, the gain in that one direction is some ratio compared to the 0 here to everywhere else. Just a little bit of like basic antenna theory stuff. So we have power of the jammer times the gain of the jammer antenna in the direction of the radar divided by 4 pi r being the distance between the jammer and the radar squared times the effective area of the radar. I just break that out. The effective area of a radar is equal to its wavelength squared divided by 4 pi times the gain of the radar antenna in the direction of the jammer. Before I move on, is there any questions or clarifications anyone would like to hit on? Yes.
How independently in a mission scenario would you determine the gain of the radar?
Say that again.
How in a mission scenario would you determine the gain of the target radar? Is it purely just based on like physical dimensions of the radar?
So how do I know what the enemy's gain is? So that's where that electronic support measure stuff comes in. So you have two options. You make guesses. You can make a relative guess by just kind of measuring in a couple places to get the directivity or field strength. If you know how much power they have to some certain approximation, and you took a measurement over there last week, but then another measurement over here at some known receiver and the radar swept and it hit here, you can kind of derive that gain ratio. But the answer is the intelligence community who gets us that information. Which is another reason why it's hard to hobby in it unless you have your own radar. But yeah, for parameters regarding your enemy radar, you're getting that through electronic support measures. Basically, you spy on them to get your solutions. Or you make general guesses.
James.
Sometimes.
James.
You can use James. You can. Anyone who's not familiar, that is a excellent series, still running. No one has the money for the modern books. They're like 1,500 euros, like 2,000, 1,200 bucks a pop. It's obnoxious. But there are publicly available large suites of just encyclopedias on military technology that have a pretty good amount of information. Get you close. But in a worst case scenario, just assume your enemy's just as good as you are and use your own capabilities. Might as well go overkill just in case. Alrighty, we'll move on from there. Also, I'm sending these slides out, so if you didn't bring a notebook and you want to remember these things, you'll have them, no problem. All right. As I said previously, there's that whole bandwidth problem. They're never going to be equal realistically, and there's not really a benefit to making them equal per se. So take that same formula that we just looked at, that whole power received at the radar from the jammer there. Oh, I went the wrong way. And all we're going to do is we're going to add the bandwidth factor, which is the bandwidth of the radar versus the bandwidth of the jammer. So we have the exact same parameters, nothing's changed except the addition of the bandwidth of the radar, bandwidth unitless, but it's often just some range of hertz. And then bandwidth of the jammer, and divide them. So, what can we derive from this? Well, if we hold everything else equal, we know that if the bandwidth of the radar is larger than the bandwidth of the jammer, your power received at the radar from the jammer goes up, which is good. We want this number to be as high as possible. We want to overpower them. Problem. What does it mean if the bandwidth of the radar is up here and the bandwidth of your jammer is down there, it means you have a narrow band jammer and they have a wide band radar. You are hitting, because higher bandwidth means they can receive more frequencies, which of course means they're going to receive more of your energy, because no guarantee it's all centered. There's going to be harmonics and stuff like that. That's just kind of how that works. But it means that if they are using a spread spectrum system, frequency hopping, stuff like that, this becomes less effective. So while this math works in a theoretical sense, in the real world, this has been defeated and you can't really run off of this rule alone. You can't just make your jammer have 0.01 hertz bandwidth and just jam anything out without a problem. This breaks down in reality, but it is applicable for theory. But we do kind of dump it really quickly, so it's whatever. All right. Now we're getting to the jamming to signal ratio, and then the next slide, we should be at the burn through. So, using the same formula, we're going to derive the radar burn through range and the jamming to signal ratio. Two formulas you need to care about: burn through range, jamming to signal ratio. That's really it. Is everyone relatively familiar with the radar equation? If not, it's basically right there. So this is the radar equation. In this case, the power received, the power received from a target at range R is this. What this means, this is actually literally just the radar equation. So all this is saying is I'm the radar, I bounce a field to you, comes back, that's my power received. That's what this whole formula does. The power of the radar's transmission, gain of the radar antenna in the direction of transmission, radar cross-section of the target, T, wavelength of the radar squared, 4 pi cubed, times the r to the 4th power, yr to the 4th power, r being the distance between you and your target. Anyone familiar with the inverse square law? Square law, I'm shooting?
Signal spreads.
Signal spread over time. I have a unit light source. It begins emission. It's in all directions like it's the sun. It goes out. As it goes out, obviously nothing in this world's perfectly parallel, so it's going to spread a bit. Spreads in a, if it goes 1 meter, it spreads 1 meter squared, and so on and so forth. So that's your r squared. Your spread is however long you went. Your spread goes like this, and that's important to capture because we're losing energy density as we go farther and farther away. That's why radars have effective ranges. You can't just go forever. And what did I just say it did? Bing, bong, does it twice. Hence the whole 4th power thing. So, if the target, so this is just, I look at plane, comes back, cool. If the target is carrying a jammer, however, the radar has to attempt to operate in a per pulse signal to ratio of this. Basically, the radar's purpose here is to ensure that this stays high. They want their signal to noise, or in this case, their signal to jammer ratio, high so they can see their signal. Our purpose is to keep the opposite true. We want our jammer to overpower their signal. So this whole derivation just flips this down. But basically, you take the radar range equation. So you got the PRT, which is right here, and PRJ, which was this formula. So what you're doing is you're taking the radar range equation divided by this, which looks ugly, but it's really not that bad. It simplifies out a bit better. Algebra. And then we get the power of the radar out, gain of the radar antenna in the direction, radar cross-section, bandwidth of the jammer, 4 pi, range between me and my target and jammer, squared, power of the jammer to me, gain of the jammer to me, bandwidth of the radar. And this is the signal to noise ratio. They need to keep this high. That's their job. If this starts dropping, I'm degrading your range. I'm getting closer to you and you can't stop me. So their job's to keep it high. Our job's to keep the opposite true. Well, everyone knows how to do an inverse. So you just take the top, put it to the bottom, and vice versa. Jammer to signal ratio. That's a write down. As Dr. Casey Kane would say, tattoo that on your body. It will be on the exam. So we got the jammer to signal ratio, which, I mean, I can say it again, but it is really just literally. So power of the jammer to me, gain of the jammer antenna to me, bandwidth of the radar, 4 pi times the distance between target and me, the radar, squared, times the power of the radar to him, times the gain of the radar's antenna to him, bandwidth of the jammer, times the radar cross-section. In my stealth slides, I did a whole derivation and discussion about what is a radar cross-section. Just think of it as the effective size that the radar sees. It's just a multiplier. Higher radar cross-section for a signal-to-noise ratio means a higher signal-to-noise. Higher radar cross-section in the case of a jammer-to-noise drops your effectiveness. Which means, funny enough, just think about it this way. All this is saying is that the vehicle is there and it's carrying a jammer. There's still energy reflecting from the vehicle back to me. And that's what I want. I'm a radar. But they're also sending the jammer, which of course stands to reason that if you're an F-22 with a super low radar cross-section, that's not great for you, because that means you are already, or great for me, because you're already reflecting so little energy back to me that your jammer is going to overpower me. So low radar cross-section vehicles excel carrying jamming systems. If you're a Boeing 737, however, this is huge. Makes it actually a lot harder to jam me because your signal's so strong relative to your jamming signal, which is kind of a problem. And it's why commercial airliners are really easy to shoot down, unfortunately.
Well, they get prioritized sometimes in the algorithms.
That's how it happens. But that's the first main thing, jammer to signal ratio. And then we can use the jamming to signal ratio to derive the burn through, which all we're really doing is reorganizing this and solving for R. Take that same formula, reorganize it, and you have this, your burn through range. All this formula right here is the mission planning gold. This is how you plan and design jammers, vehicles, missions. Yep.
What does that burn through mean?
So it's the word, the term they use for it. All it basically means is, so here's my jamming system, all the radar stuff's factored in. I'm a plane, I'm a radar. Burn through range is, let's say it's right in the middle of these 2 points. If you are farther than the burn through range, the jammer is sufficient to cloak your presence. The jammer will overpower your signal return such that you will be fine. The second you pass it, the radar burns through, and your jammer is no longer effective at shielding you. And you are fully visible and targetable at that point. So this is what keeps you from getting yourself shot out of the sky. The whole point of stealth, electronic warfare, all these things, if you're really good at it, is to just easily just swipe out enemy air defenses. It's awesome. In real life though, against near peer adversaries, it's a different ballgame. You're never gonna fully defeat their capabilities. I like to think we're that good, but nobody's that good. When billions of dollars are on the line and tens of thousands of people are spending their entire careers working on this stuff, you kind of get neck and neck on these things. The whole point of stealth, jammers, electronic warfare, is to reduce effective range. If I design my radar system to cover the entire continental United States, and I'm like, it's the iron wall, no one's getting through this, and then someone just does a little bit of this, there's gaps. And what do? Just fly through the gaps. Not a problem, right? Simple. And that's how they do it. From a mission planning perspective and a design perspective, this is how you do this stuff. So you know your jammer to signal ratio. That's going to come from SIGINT. That's going to come from all the stuff we calculated previously. All these parameters, cross sections, all that stuff. Boom. You know the safe distance at which there and beyond you're fine. Past it, you're risking getting shot down. That's a really great formula. And keep in mind, while we're talking about noise jamming, all these things exist for every type of jammer. It just so happens that the math gets worse the more complicated you go. But this is the fundamental idea. For every single jamming system, there's a burn-through relationship, there's a jammer to signal relationship, and it's super awesome to have those because that's what lets you design your platforms. Target-like. This is the cream of the crop. Noise-like jammers worked in the past, but struggle now. Nowadays, one, it's easy to see if someone's using a noise-type jammer. It's super simple to detect. It's in fact automatically detectable. You're immediately able to discern this is just a loud beacon and it is wasting my time and is trying to slow me down. Most radar systems can filter it. They can adjust their beams with spatial filtering to ignore it. Noise jamming is weak. Target-like jamming, however, this is how it's done. So, and it's really cool. If the radiated jamming signal, my signal sending out to my target, is similar to the signal that would have been scattered by me otherwise, as in it's close to the radar signature of my aircraft, the jamming type is called target-like. Traditionally, one or more characteristics of the radiated jamming signal are tweaked to deceive the enemy radar. And we'll get into how cool that is in a second. I have a whole list of all the parameters and what kinds of deception and errors they can introduce in a radar system. But since target-like jamming signals can be identical to target returns, a radar cannot reduce the jamming to signal ratio by integrating many target pulses. With noise and pulse jammers, over time, radars can build a map and do what it just says here, integrate. You can use simple mathematical operations to slowly adapt your system and be like, okay, I get it, and ignore it. As I mentioned, you can beat it with math if you're noise-like. What's the problem with target-like? Well, it looks like a target, which means radar systems cannot afford to simply ignore it. There are discrimination algorithms and there's stuff that exists that gets good and close to these things, and that's heavily based on intelligence. The better your intelligence networks are, the better map you have of your enemy's capabilities, cross-sections, signatures. That lets you get better at beating deception. But most of the time, if you're doing good deception, they have no choice but to deal with the fake signature. They cannot afford to ignore it because for all they know, it's real. And this is why it's a far more powerful technique. So we'll start with some basic circuits, very simple. A common method to generate these, and I can vouch for the fact that this is absolutely still used, just in a more advanced manner, is very simple. You have a receive antenna on the vehicle, listening for radars. You get a radar signal in, you receive it, you send it through an amplifier with some gain, just multiply the signal, boost it, and then you transmit it right back. Simple, you just went. Well, you may say, well, what's the point? All you did was give yourself away harder. You multiplied what would have just been normal. And the answer to that is yes. If you do this, you just killed yourself, basically. So don't do this. That's not what you want to do. But this repeater system, these are called repeater systems, will generate a jamming to signal ratio at the threat radar as follows. Whenever you say that, so that means math. So, as I said, every one of these systems has a jamming to signal ratio. It has a burn through range, all that kind of stuff. So for this one, we recognize this. So the power of the jammer received at the radar. We remember this portion. Power of the radar goes out, gain of the radar in the direction of my target, or of my jammer, 4 pi r squared, wavelength, gain of the jammer, this is new, gain of that received jammer antenna in the direction of the radar. That's what GJR means. Just more gain multipliers. Whenever you introduce an antenna, you introduce a gain multiplier. Just keep that in mind. Anytime you introduce an antenna in a system, you must factor in your gain. And that's directional antenna gain. Divided by 4 pi. This G here is just the gain of the amplifier. That triangle we saw. Gain of the jammer in the direction, jammer antenna in the direction of the target, which is us. Now the jammer is sending back out, so the repeat loop was he comes in off that antenna. This G is that boost. This one is that antenna heading back out. Divided by 4 pi r squared times wavelength squared over 4 pi times the total gain of the radar antenna in the direction of the target and the jammer. This all simplifies out, luckily. Oh, sorry, no, I lied. This is the power of the jammer received at the radar, and this is the power of the return from the target received at the radar. This is what the radar wants. This is what we want. So this is similar to that radar equation previously. You know, radar cross-section, gain here, same thing, same thing. Oh, sorry, never mind. This literally is the, this is just an expanded version of the radar equation, because the radar equation is 4 pi cubed r to the 4th power. Yeah, okay, we're good. That's normal, we saw that already. And the jammer to signal ratio for such repeater systems actually comes out to be pretty simple, just a bunch of gains and a radar cross section. So the jammer to signal is wavelength squared over 4 pi, gain of the jammer in the direction of the jammer receive antenna in the direction of the radar, times that amplifier gain, times the jammer transmit antenna in the direction of the radar, divided by the cross section of the vehicle. Again, whenever you're talking jammer to signal ratios, the cross section of the vehicle is always going to be in the denominator. The smaller the cross section, the better your jammer to signal ratio is, which is why modern stealth platforms are so good at jamming. Now we start, as I said, the previous one you just get yourself killed. This one, however, significantly better. I don't think I actually, did I do more formulas? Just a little bit. So, there's a lot of issues with the simple repeater, but a really easy one is, these guys are relatively close together, that whole receive and transmit, and it's just a closed loop amplifier. The second you transmit, you're gonna hear yourself and just go into a loop of amplifying yourself. So you're gonna oscillate, you're gonna grow without bound, and it's really not a good look. So instead, that means that you'd be limited to a gain of 1, which is not awesome, because a gain any higher than 1 would result in your thing just looping and being a problem. In addition to the fact that you're just blasting out the receive signal from yourself stronger and making it easier to shoot you down. This, however, start getting more complicated. Same antennas, same amplifier square, that's what that previous one is, another type of amplifier. Then we have this comparison block and a voltage-controlled oscillator to tune frequencies. This is where it gets clever. This is the next level of repeat jammers, and they are called keyed oscillator transponders. And that's a simplified block diagram of it. This is the new jamming to signal. We're not going to go through the full re-derivation again. When you do this, you get to cut out a lot of those extra gain factors, and you just get 4 pi r squared over the radar cross-section of your target times the ratio of the gain of your jammer antenna versus your radar antenna coming at you times the ratio of your power of your jammer to the power of your target signal. And that's where you are. Okay, that's fine. Now we keep pushing it. This is a full implementation of target-like jamming. Amplifier, controllable delay lines, frequency offset control, power amplifiers, modulators for the amplitudes, polarization control. These are all the variables that controlling is useful for. So I think we're good on formulas. I don't think I have any more math to hurt anyone today. But this system, and the more advanced ones fielded today, are capable of manipulating the input signal in ways so we don't get shot down. And the corresponding effects are as follows. So, first things first, you don't just want to blast out a beacon into the air and give away your exact position. Okay, what do you do to fix that? Add a time delay. Signal comes in, you wait a second, and then broadcast it. Or, assuming it's periodic, or you do another trick, which is they keep blasting pulses at you. You can grab a pulse, record it, and then replay it at an opportune time to appear as if you are advancing in time. So instead of waiting, to the radar, it looks like you've traveled forward in time to them. You've emitted, they've received a signal faster than they expected. Advancing a signal makes you look like you're way closer than you are. Delaying a signal makes you look like you're way farther than you are. That generates an error in the range, also known as where you are, your position in space. And the actual errors are called range gate walk-off, generating a false target. This keeps you from getting shot down. Their missiles, their interceptors, they're going to just go to some random place in space because you're not there. But they think you are. Next step, that whole frequency. Frequency or phase. This creates errors in velocity. This can trick them into seeing you moving faster or slower than you are. Obviously, if we just had an F-22 with the radar cross-section of a bumblebee flying at Mach 3 through the air, it does not matter how good the stealth coding is, nor does it matter that the radar sees something the size of a bumblebee. It's moving at Mach 3. That's pretty obvious that it is not a bumblebee, nor is it clutter or noise. So it's important to cloak your velocity. Normally, Doppler effects would prevent that, but as I said, lower cross-section vehicles, it's way easier to trick things because your return signal is so weak compared to the one you create. So by modulating the phase or the frequency, which for anyone who knows is just Doppler effects, if you're moving fast towards the signal, frequency compresses and increases, and if you're moving fast away, it expands and decreases. Redshift, blue shift, that kind of thing. You create an error in velocity, which is titled or known as velocity gate walk-off, again, false target generation. These, you pick your poison. They all do the same thing. Certain antennae are more vulnerable to certain versions of these. But amplitude modulation, polarization control, and multiple sources all create errors in the angle of perceived signal. This is super important because if you're just changing range, all you did was tell them where you are in the past or the future, because range is just a line. So if they're tracking you and you're creating errors in range, you're just going to basically send a fake signature forward or backward from where you were headed, because the viewing angle is the same in spherical coordinate system. You're just moving along a line in space. But if you also mess with the angle, you could send them on a wild goose chase hundreds of miles away. And that's what these are for. So if you do amplitude modulation, you can create errors in angle through sequential lobing and automatic gain control effects. Through polarization control, this is known as cross-pole jamming. Super effective against Russian stuff in the past, and since they haven't really changed much, it's still effective against Russian stuff. Creates errors in angles, and it's the cross-polarization of radar antennas. Finally, multiple sources. This is if you're like super rich like the United States militarily, and you can just afford to field like 3,000 planes into the air at any given time. Also creates an error in angle of arrival. Right? All right. So that's that for target-like jamming. Cool. All right. Yeah.
What kind of effect does like radar beam steering have on that? Because if you're starting to fake out your position or your angle, the radar beam is going to steer off, and all of a sudden your jamming signal is not really as effective, or it's not getting enough energy into the radar.
Well, if the beam steers away, your receive antenna no longer receives it, so you'll stop jamming. So they'll see you disappear, unless you keep doing it. And some systems do. They'll record the signal and keep playing it back. But as you said, it will be weaker, assuming that they don't have massive grading lobes and that they're steering it away, so the gain's dropping. But again, deception is deception. They've wasted valuable time looking where you're not. And when they do find you again, they're just going to be like, oh, he's over there now. It does have an effect. You're right. It would stop jamming, start jamming. It's just, again, confusion, deception. It can become a huge issue. And if you have dedicated systems focused to suppressing radars with that, and they're not trying to just save themselves, they're trying to suppress so someone else can come in and get some work done, it can become really difficult. That's when that multiple source stuff comes in. You start just fielding a whole bunch of these guys and just keeping people down. Yep.
So on the last slide, it was kind of clear to me how polarization changed the angle, but how does amplitude change the angle? Like, does that make sense? Can you say?
It's a good question. An excellent question.
If I had to guess, it has to do with the directional gain of the antenna. So if they're expecting to see, your amplitude coming back in the center of your lobe, you're going to see the highest amplitude. Where if you're at the edge of their lobe, it'll be weaker. That's my guess at it.
I might not even find it in time. Yeah. Some way.
There is some way to do it.
Yeah. That table came right out of here. They might not have even mentioned why that one specifically works. I do know that this text does reference specifically cross-pole jamming, multiple source jamming, frequency phase jamming, or all these, not jamming, but these manipulations, and time delay and advanced jamming. I could make guesses as to why amplitude works, but I'm not gonna potentially lie. But the book said so.
given that the book says sequential lobing, I think he's on the right track with it, that you're on the right track with
Yeah.
why it
Again, that's a guess. I'm not, I never work on this stuff, so I'm like,
No, yeah, no.
we can kind of make
It's actually
guesses.
similar to what you said and what you said. If you are modulating the amplitude, which means it's changing over time, if the radar is still looking in your direction and it sees an amplitude start going down, it's going to think it's lost you. So it's going to start looking in different directions based on whichever algorithms it uses to track, which is going to create viewing angle or arrival angle differences. Because they had a fake range, and then with that fake range, they also see an amplitude drop off. That's going to mean it's a fake direction with that fake velocity, and that's going to create that angle difference, and they're going to start looking in the wrong place.
Okay, so then when your radar power goes down and the beam is steered off of you, if you increase your amplitude, it thinks it's quote unquote.
It's going to think you're tracking, yeah.
It's on track.
Like if
yeah.
it starts steering away and it's boosting its amplitude, it's going to think it's still on point. So it's going to start looking in the wrong direction.
So is the polarization jamming, is that where you get like a TE wave and you send back like a TM wave?
Yeah, like if you have like a right hand or a right hand circular and it comes in and you blast them with like a left hand or something. It's just varying polarizations. Often what you do want is you want the 90-degree polarization difference. It'll introduce small angular variations, often on the order of like 3 to 5 degrees. There's actually a whole there's a YouTuber, he's like some British guy, but he's Canadian. And he has like a 17 video series on cross-pole jamming, and it's like it's got like 2,000 views. It's like the weirdest thing I've ever seen, but he knows his stuff.
That was more classification than brains, like your meme at the beginning.
Exactly.
Back on the amplitude one, the other thing that could be happening is a lot of times when you're looking at radars, you see this nice smooth gain pattern, but if you keep going, it actually has zeros
Oscillations.
and lows. And if you're coming in, say on the side, outside the main beam width, but you're really blasting some signal,
Yeah, you're hitting like a
the
grading
side
lobe or a
lobe, the
side
side
lobe.
lobe will pick it up, and the radar will think you're in the main beam.
And actually, we'll have a radiation pattern coming up soon for one of the countermeasure systems. But we are running out of time, so I want to make sure I get through everything. All right. So we talked active, which is noise like, target like. Now we're hitting passive. I'm pretty sure this is literally like the one slide I have on this. Passive ECM techniques are methods to reduce the effectiveness of enemy radar systems without actively doing anything. The most common is just observable reduction and clutter enhancement. Observable reduction is stealth. Reduce your radar cross-section, emit or reflect less energy back to your enemy or system. Clutter enhancement, aka chaff, just drop a bunch of tiny metal dipoles into the air, and now the signature is massive and it is super difficult to discern what is chaff and what is vehicle. However, because they are functionally metal confetti, they slow down very quickly. You will lose your chaff fast. It's a momentary measure. You'll basically never be able to have chaff that stays on you and shields you. It's kind of, think of it as, I say it here, a radar flare. You got a couple of them on your vehicle for emergency situations. When everything else fails, you start popping chaff off and hope they hit the metal instead of you. All right, countermeasures. ECCM, also known as electronic defense, is focused on counteracting all these attack measures we've been talking about. So we've been talking about how overpowering and ridiculous these attack measures are and how you could just take over a country. Unfortunately, it's not actually the case because there's a defense to go along with that attack. The following slide just lists a ridiculous amount of ECCM techniques, relatively categorized. You've got filtering techniques. All these are methods to filter signals that you expect and don't expect, so you can spend time only looking at the stuff you care about. Spatial filtering. This is the one that actually matters the most, and this is the one that actually is responsible for making noise jamming functionally useless. Multiple measurements. This helps with noise jamming, pulse jamming, and it allows you to do that whole integrate, get rid of the noise jamming. It can let you, over time, discern things that were momentary deceptions, but if you keep looking, it keeps getting faster on different bands, you can start to realize that's fake, that kind of stuff. Saturation elimination, this prevents me from just maxing out your receiver. You can tweak your gains, that kind of stuff, so I don't just blast you out. And operator displays, things like spectrum analyzers and additional displays. At the end of the day, radars, while they can operate automatically, are predominantly operated by personnel. Humans make the decisions, and humans are ultimately responsible for discerning what's going on. So by giving them additional tools like spectrum analyzers and stuff to allow them to kind of visualize the electromagnetic domain that they're in, they can catch some of the tricks. And there's entire training manuals on that, but they are classified, unfortunately. So, yeah, we're gonna do a quick concept explanation as to why spatial filtering is super common and also super useful. This is like the only slide I have for this. So, we were talking about antenna patterns earlier. This is a great little picture. This is the main lobe of your antenna. Think of this as, by the way, this is a 2D linear array antenna. That means if we were to kind of go back below here, there'd be a couple antennas. This looks like the radiation pattern of probably 9 to 12 elements in a row. So there's all these elements here, and they all emit the same signal, but because it is off kilter, they are emitting the signals at a slight phase delay. So he emits first, next, and that results in the overall destructive constructive pattern beam forming that way. This alone is a great career path to be in. Highly recommend it, super cool stuff. But we have a main beam. This is what we're steering to look around. And we have these side lobes that we don't really want, but you can only do so much to suppress them. This is actually a pretty terrible antenna, realistically, because these side lobes are huge.
Yeah.
In real life, you'd want these things to be like 60, 80 dB down if you could help it. But we've got a jammer source. In this case, it's a speaker, but let's say it's one of those noise jammers we were talking about. And right now, he is emitting in the direction of the main lobe. So this radar is just getting blasted by this, and it's like, I can't see anything, I don't know what's going on. All it has to do is use spatial filtering to reevaluate the phase shifts of these antennas to steer the beam slightly away, still looking in the direction of the jammer to try and catch stuff behind it, near it, or the vehicle itself. But if it steers such that the primary lobe, so this is the antenna lobe of our antenna, imagine, since this is also an antenna, there's another pattern coming this way. If we steer this beam such that the incoming energy at the peak of the jammer hits what are called nodes, the jamming's gone. In every phased array or array antenna, it has side lobes and nodes. Normally, side lobes are horrible, we don't want them, but luckily they do come with the added benefit of nodes. If you steer your beam in such a way that a node is directly facing the bore site of a jammer, jammer doesn't affect you anymore. Because the node is called a node because it has 0 or less dB of gain. So it doesn't see it. And this is super common, and it's super powerful. Just like 2 months ago, it was at the other ECM Society talk. They brought a professor in who literally had a whole 80 slide deck just about spatial filtering. It was ridiculous, but it was cool. So this is a technique that can really ensure that you don't get obliterated by jammers. And as I said, there's a lot of ways to protect yourself, and there's a lot of ways to attack people too, just like anything else. And that's kind of how it goes. Don't have time for this. We're already at time, technically. So that's that. Q&A. So I've got the Q&A slide up, but all right, do that real quick while we're talking Q&A. So anybody got questions, comments, concerns, hopes, dreams, anger?
The math that triggered me.
Fear? Anything at all?
So the spatial filtering essentially lets you avoid the jamming signal, assuming you don't want to track the thing emitting the jamming signal.
So, sort of. So you can actually do some tricks, assuming you have a really nice phased array. We're talking a couple thousand elements. Your beam is so precise that you can actually steer the beam continuously around the jammer while keeping a node focused on the jammer, such that you can track the vehicle but ignore the jammer.
Even with that kind of angular discrimination?
Assuming the jammer isn't massive.
Yeah.
It depends on how nice your radar is and how strong their jammer is. Because at the end of the day, jammer also does not want to just go everywhere because you hit yourself. So both people are trying to balance the whole, I want to jam you, but I don't want to hit myself, or I want to see you, but I don't want to get jammed. So they're both tweaking constantly their own angular resolution, gains, positioning of their beams. It's ridiculous. It's like literal like laser wars in the air, constantly being fought by supercomputers. And that's just one plane, one radar.
So like modern EW pods is like a single below the plane element. Are there any modern systems that have like multiple jammer transmitters on a single vehicle to try to prevent that kind of thing?
From the knowledge that I have in a public domain, the answer is there are towed jammers. They can have more than one towed jammer or a decoy. There are platforms that exist that are just jammers on their own. Like an ADBM mauled cruise missile is just a jammer and deceiver. So it's its own flying vehicle whose sole purpose is to deceive and jam. And your plane could carry those. I'm fairly certain the F-35 has several towed jammer systems and has several arrays dedicated to receiving environmental information. So it's loaded up with sensors, it sees everything, and then it can feed that through a fiber line to its towed jammers. They call them towed decoys, but really it's all just decoy is still a jammer.
I came a little.
Oh, 1 second. Were you good?
Yeah.
Okay, good. Just making sure. What's up?
I came a little late, so I didn't hear. What was your degree again?
So I have a bachelor's in electrical engineering from UAH. I'm getting my master's part-time here in electrical engineering as well. And I work full-time at Northrop Grumman as a Tempest engineer. Also, it is the end. You can ask me what a Tempest engineer is now, if you are so inclined.
What's a Tempest engineer, Ethan?
No, someone else has to ask. You know.
What's a Tempest engineer?
You know too. What do you got?
What's a Tempest engineer?
Interesting you ask. So, Tempest, I actually highly recommend this field because if we don't get some more people into it in time, everyone's going to be screwed, except for the Tempest engineers who will be paid very handsomely for their services. But
That's correct.
it is correct. Tempest is a NSA code word, formerly classified, now not classified. It means nothing. If you look it up on Wikipedia, it will say it is an acronym. It is not an acronym. And if you say that in front of a professional Tempest engineer, prepare to get Batista bombed into the floor, because it's not going to go well. But Tempest is a discipline in which we are concerned with protecting classified signals and information from unintentionally emanating and leaking in the RF domain. So basically, let's just say a very common Tempest demo is this screen right now has a picture on it. I could, because this is not Tempest shielded or mitigated, stand several rooms over with an antenna and get exactly what's on this screen. Same with your keyboard. If anyone's ever heard about the NSA being able to get your exact keystrokes through the air, through audio, all these things, it's basically spying. So Tempest is to mitigate spying electrically, like RF and radio spying, but we do so by spying on our own equipment to see how vulnerable it is, and then we fix it. That's our job.
What books in the public domain would you learn about Tempest?
Tempest? Sadly, none. If you want to get started in Tempest from a career standpoint, what you do is you look up the redacted, unclassified NISTISM 192 Tempest spec. NISTISM is NSTISSAM, NISTISM. And read that to kind of get an understanding for what it is, but it's redacted and classified. Tempest as a discipline, because it is effective techniques to spy on classified information, is classified in and of itself. Because it's so hard to get into, there are only 100 certified Tempest professionals on Earth. Currently, about 40 of them are going to retire in the next 5 years. And Tempest is legally required on every single DoD program. So there's not enough people to do the legally required job. And let's just say if you are a certified Tempest professional, you get paid a lot. And in addition to that, the certifying body is the NSA. The test is extraordinarily difficult. You have to study for a couple years and work under a currently certified professional to take the exam. And when it is exam time, they fly you up to the NSA for 2 days, and it's a 2-day long exam. It's a whole thing. And there's 2 levels, level 1, level 2.
There are research papers from academics that study emanations like that I guess may not be technically Tempest.
Like rasterization and stuff.
Yeah.
There is stuff, like Tempest did not originate on its own, it originated from Bell Labs figuring out how noisy old switches were. And they realized, oh no, the cryptography key's just in the air. That's not good. But with regards to texts, everyone sign in, sign out? Alright, good. So you're hooked. Where do you learn more? So, for this, not just for Tempest, just in general. For electronic warfare, at the end of the day, what it really is just advanced antenna and signals. Electronic warfare is just an application of the underlying fundamental knowledge of antennas and signals. That's really all it is. So, you can get yourself really well situated to get into this field if you are so inclined by taking predominantly electrical engineering courses, antenna design, fundamentals of radars, radar systems, radar tracking, radar waveform signal processing. It's just how it is class-wise. But, as I mentioned previously, I recommend this specific text, Radar Electronic Warfare by August Golden Jr. Excellent book. Basically all the slides and math came from here, and there is way more in here. It gets like a lot. It does focus predominantly on attack measures though. Defense is like a whole ball game and it's like really hard, but it's a good book and it's a really good intro and it does explain things fairly decently. At the end of the day, there are a lot of fields in science and engineering that are extraordinarily valuable and important to modern defense. Advanced discrimination techniques, stealth technology, guidance, navigation, and control. They're difficult to get into as a career field because they're extraordinarily classified. At the high levels, you can't just take a class on it and know it. Your options are join the military. Your options are join the military, get a PhD and get DoD funding to research it so you can learn about it at school, or study the fundamentals to the point where you are confident in interviewing well and getting entry-level positions and working your way into it. You can get right out of college jobs right in these fields. It's not unheard of. It is tricky because at the end of the day, these topics are hard. And when you get into that interview room with the 30-year vet RF guy, and he's like, "I need you to integrate this sync function right now," you're gonna vomit a little bit. But my buddy who did vomit a little bit got the job anyway, so it's fine. But at the end of the day, it's hard, but it's fulfilling, and it is really top of the line work. And if you are interested, your options to learn are take higher level courses to get fundamentals down, save up some money to buy these books. So I just showed off this text, but in the next slide there's references, but there's various books you can buy that help with this. Anti-jamming, synthetic aperture stuff, electronic intelligence. And funny enough, while outdated, the government does publish its own texts. This is from Naval Air Command, the Electronic Warfare and Radar Systems Engineering Handbook, designed to take you from zero to hero. Right? Introduction, fundamentals, antennas, radar equations, it goes through everything. RF components, electro-optics is great. You can buy this online, it's $40.
How much of that is outdated on purpose?
That's a good question. The answer is almost all of it. I mean, they wait like 40 years to release it because it's bad. But also, so that's the other thing. You can Google stuff, but I caution against it. I recommend buying books that are verified and published by researchers and respected experts in the field, because the internet is full of liars. And they will 100% and do put fake shit out there on purpose just to obfuscate stuff. Any intelligence agency would love if their fake doctored report on radar cross-sections gets taken up as real intelligence from some adversary and then just completely destroys their defensive stance because they're operating off of nonsense, right? And we do that all the time, right? So that's important. But if you do want to work on stuff like this as a career, it is DoD. At the end of the day, it is cleared stuff. Even in academia, they're still gonna make you get a clearance to give you that grant. It's just how it is, unfortunate. So these are the references. The reason I have those QR code scans is because as long as I got your email through one of those, I'll send out these slides to you. It's like your proof of attendance, so you can have these. Good. Yeah, there's a lot of stuff. Good stuff. A good publisher on Radar Tech, our Tech House, they have a lot of excellent stuff. I believe it's a British publisher, but I believe they have an American wing now. But they publish a lot of radar stuff, and they've got some even cutting-edge modern research topics. But how many people here are UH students or were UH students? See, one of the benefits of that is that you have free access to IEEE Explore, which is an excellent source of up-to-date modern research through the UH Salmon Library. You can literally go on there and type radar cross-section reduction absorber, and then it'll just like 20 papers will come up, be like, here's how you make a stealth bomb, kiddo. And it's great. That's awesome. That's how it's
In
done.
MATLAB.
In MATLAB, even better.
For the basics, I would also recommend either of the Skolnick books, the Intro to Radar Systems and the Radar Handbook especially. If you're gonna work in radar, it's worth the money to get the Radar Handbook. It is about...
You don't need to spend that much. You can get the...
Yeah.
Well, first off, the PDF's right here, so it's just free. Yeah, there it is. But if you do like physical copies, I have a large library, I'm a big fan of physical copies. You can get, as he mentioned, Skolnick's texts. The first edition and the second edition cost anywhere from $20 to $40 on used textbook sites. And of course, you can have the most up-to-date one for free.
I love just search engines
Yeah,
stealing
it's
stuff from
easy.
random FTP sites.
I think it's on its 4th edition now, but
Yeah,
another good reference is Introduction to Airborne Radar Systems by Stimson is another excellent one. He worked at whatever it was Hughes at the time. I don't know who owns them now, but yeah, Intro to Airborne Radar. That is an excellent reference. And the Skolnick and the Stimson are general radar references, and they cover everything at a somewhere to the intro level to a fairly detailed. You can be essentially a systems engineer with those 3 texts.
There he is. I have 2 of those. Whoever asked me the best question, I'll give you 1 book. I have 2 copies of this one. All right. Any other questions? I have 4 business cards that I forgot to get rid of. Who wants a business card?
Oh, actually, I already have one.
First come, first serve on the business card. Enjoy. All right. Anything else? Otherwise, dismissed. I will send out I think I've already sent out the schedule to everybody through the email blast to the university. But the next talk is in 2 weeks. Same place, same time, 7:30. This room. So 2 weeks from now exactly, just next Thursday. It's given by Cummings Aerospace Engineer Sean Mitchell. What's the title?
Introduction to Automated Target Recognition and Tracking.
So we're shooting planes down. Introduction to Automated Target Recognition and Tracking, 7:30 p.m. SST 150 here, 2 weeks, 2 Thursdays from now.
Is that radar or EOIR?
Computer vision type approach.
The bounty
And then-
scene from Terminator.
So that's August 3rd, if I remember correctly, date-wise. And then August 20th, I think, is the next 2 Thursdays.
April.
Yes, April. Better. I believe that is same place, same time. 2 weeks from that talk is Stealth Design Principles presented by me. It'll be an extension of all the stuff from these stealth slides last semester, kind of a bit of the electronic warfare stuff here, and it'll focus predominantly on how do you make a vehicle passively stealthy with a reduced signature. Shaping, material composition, that kind of stuff. So it'd be cool. Those are the next talks. All right, thank you everyone for coming. I will send out these slides as soon as I remember to.